Hello, everyone. Welcome to the 8th lecture. And this is really an important lecture. We are going to learn a lot and continue to learn about synchronization and how we are going to solve the problems and ensure provides a critical section abstraction and synchronization primitives. So let's recall a few things from the last time, in particular semaphores. And if you remember, semaphores are like generalized locks, and they were defined many years ago, like 60 years ago, almost. And it was a main synchronization primitive used in original Unix. And when we are talking here about synchronization, we are talking about in the context of implementing a critical section. If you remember, a critical section, it's a sequence of code in which only one thread can be active at a given time. So therefore, if one thread is active in a critical section, the other threads which want to enter the critical section to execute the code, they need to wait, right? So you need a mechanism to synchronize this kind of entrance to the critical section. And then when a thread exits the critical section, another thread from the waiting ones is going to enter the critical section, okay? And there are two primitives, P and V. P is if the semaphore is 0, if P is waiting. If the semaphore is greater than 0, it decrements it. And the other one, V, it's just increment the semaphore by 1. And if the semaphore was 0, and if it's incremented to 1, then it's going to wake up one of the threads which was waiting on a semaphore, if any. Okay. And these are two use of the semaphores we went over last time. One is mutual exclusion. So it's again, this is about implementing critical sections. And here it's very simple. You are going to initialize the semaphore to 1, and then you put before and after critical section a P and a V. So the first thread, which is going to execute the instruction P, the semaphore is 1, is going to decrement it, is going to enter the critical section. If another thread comes and try to execute the code, the semaphore now is 0, so it has to wait. When the first semaphore exits the critical section, it's calling V, and V is incrementing the semaphore, and therefore, as a result, we signal the thread who is waiting to enter the critical section. Right? And it's also the scheduling constraints. And this is basically, we want to signal, to wait for a thread or signal a thread to do something. And here the initial value is 0. And the classic example is a join implementation for the thread. You remember that with a join, the parent, the thread which executes the join waits for another thread to finish. Okay. And so basically the thread which waits to finish, the join, they use to implement this, to use the same semaphore. So the thread, you initialize the semaphore to 0, and the thread who waits for another thread to join, to finish, then it's just calling P, right? And if the other thread, and the other thread, when it finishes, is calling V. Okay, so if the thread hasn't finished, the semaphore is 0. So the join operation will just wait. And it will wait until when? Until the thread it's waiting for, it's executing this thread finish, which calls V, it's incrementing the semaphore to 1, which means that, and signals the waiting thread, and the waiting thread now the semaphore is 1, and going to start executing and decrementing it to 0, and finish the code, finish the join operation. Okay. Any questions? Okay, please ask any questions, if you have any. So, and then we went to this bounded buffer. So you remember the bounded buffer, we have a bunch of producers, a bunch of consumers. The producer put elements in the buffer, the consumers get elements around the buffer. And you hear, if you look at the constraints, what we are talking about here is that for the consumer must wait for the producer to fill the buffer. If the buffer is empty, then the consumer have to wait. On the other hand, the producers must wait for the consumer to empty the buffer. If the buffer is full, then the producer has to wait because there are no place in the buffer to put new elements. And there is the buffer itself manipulating the buffer or the queue. It's a critical section, and only one thread is going to manipulate the queue, right? Either one consumer or one producer, right? Okay. So how we are going to implement it? We are going for each of these constraints. We are going to use a semaphore. So we are going to use a semaphore for full buffers. This is consumer constraint, and empty buffers. Okay. And basically each of the semaphore at a given time will show how many elements are in the buffer, full buffers, and how many elements you can still put in the buffer. So basically, if you add to these two semaphores, you should get the total number of elements, that buffer size. And then a mutex, a semaphore mutex for the mutual exclusion, to make sure that you have only one thread manipulating the queue, that is whether inserting a new element or removing an element from the queue. Okay, so let's start. So full slots is basically 0 because initially there is nothing in the queue. Empty slots is the buffer size. So remember, if you add here full slots with empty slots, you get the size of the buffer. And mutex is 1, right? That no one is in the critical section. And the producer then is very simple, right? It's like basically you are waiting for slots to be available, and then you use a mutex to protect the critical section. And then once you are done, you are incrementing the number of slots or full slots, right? Because you added one element. And the consumer is very similar. You are waiting for full slots to be greater than 0. This means that there is at least one element in the buffer. So if you have more than one element in the buffer, you can dequeue that element. Again, the dequeue operation is protected by the mutex. And then once you are done, you are going to increment the empty slots because now it's one more available slots in the queue. Okay, and return the item. Okay, so that's basically here. You use a mutex to protect the critical section. So therefore, no two threads at the same time operates on the queue to manipulate the pointers, to remove the elements or to add the element to the queue. And then the other one are scheduling constraints of full slots. It's incremented by the producer, and then it's decremented by the consumer. And similarly, the empty space is incremented by the consumer and decremented by the producer. Okay. Any questions? Okay. So a discussion about solution. So you can see there is a symmetry, right? The producer is calling P and then V on empty buffers and full buffers. And the consumer does the reverse. Is calling P on the full buffers and V on the empty buffers, right? So there is this asymmetry, okay? And it's exactly what we expect, right? Because the producer has to decrease the number of empty slots and increase the number of occupied slots. And the consumer, the producer has to wait for, the producer, yeah. it has to wait for empty slots to be available, but then once you put the element, you decrease the number of empty slots and you increase the numbers of occupied slots, and the consumer is the other way around. When there is at least one element in the buffer, you decrease the number of occupied slots because you take one element, and then also this increase the number of empty slots, right? So now this is a question for you. And if, you know, there is there, you remember in the original code, let me just move this. We call first, producer calls first a semaphore P on the empty slots and then the mutex. Now, is that order important? Okay, that's a question for the class. So looking forward to your replies, to your answers. Yes, it is. If you do this, it can be, we can deadlock. Can someone explain how you can get the deadlock here? It's very simple. Yes. Thank you, Aaron and Akshay. So basically, it's very simple, right? For instance, you imagine that you're a producer and the empty slots, there are no empty slots. Okay? So empty slots is 0. So what happens? You acquire the mutex for the critical section, and then you are going to start waiting because empty slots is 0, right? There is no place in the queue to insert a new element, to add a new element. But now you are going to wait in the critical section. And the only way the empty slots can be incremented is by the consumer, okay? But in order to do that, the consumer has to, the consumer has to dequeue an operation, but for that you need to acquire mutex. But you own the mutex, the producer owns the mutex, so you cannot acquire the mutex because you can have only one thread in the critical section. So therefore, consumer cannot dequeue any element, and therefore the producer will continue to wait for the empty slots to be incremented, which will never happen. Okay, very good. Is the order of V important? Well, I have the answer here is that, yeah, no, because you just do the increment. What if you have 2 producers and 2 consumers? Is this, do you need, any changes to this code? I mean, to the previous code, which is working, not to this one. So assuming that somehow P and mutex and empty slots are not reordered. So do you need to make any changes to this code? If we have 2 producers and 2 consumers. Yes, Sonali, you are correct. No, you don't need to do it to make any change. It's going just to work. And the reason it's going to work, it's again because no matter how many consumer and producers you are going to have, you can it's only one of those can be in the critical section. Yes, exactly. Thank you. Good. So so it's again, so you can see that P and V are synchronization primitives. And now what we are going to do in the rest of these lectures, we are going to try to figure out how to implement these synchronization primitives. Okay, synchronization primitive P and V are at the higher level, but at the low level, you have what you have on your in the when you are talking about the processor. What are what you can do? You can execute instructions like load and stores, and you can disable interrupts. And then we'll see there are a few other specialized instructions like test and set and compare and swap, which would make it much easier to implement higher level synchronization primitives. Because like you'll see, using just load and store and disable interrupts, they are not ideal solutions, right? Then at the higher level, we have logs. We discussed last time. We are going to discuss more this lecture, semaphores, and then monitors, and send receives operation. But we are going to discuss log semaphores, their implementation, and hopefully you are going to also get to monitors during this lecture. And then programs is a higher. There are higher abstraction at the program level, and we are not going to talk about them at least this week. And here is a motivating example, okay? And if you haven't paid too much attention until now, please from now on for these examples, pay attention because it will learn you a lot. And remember that, next Wednesday, we have the first midterm, okay? And this and the next lecture are going to be part of the topics covered by the midterm, okay? So here is a problem. And basically the problem is that there are two roommates and both of them like milk. And the problem is that, if there is no milk in the fridge, then whoever discovers that, they are going to go and get milk, right? And the goal here is to not get too much milk. And how can you get too much milk? Well, think about the same sequence of events. At 3 o'clock, first roommate, let's call her person A, look in the fridge, there is no milk. So leaves to goes to the store. And at this time, and while arriving at the store, it's a closed store, the second roommate, call her person B, look at the fridge and it's out of milk. So she's going to do the same thing, leave for store and arrive at store. And during this time, the person A left the store, arrived home, put the milk in the fridge, while the person B is at the store buying milk. And then we are going to get, at the end of the day, we are going to have 2 bottles of milks in the fridge. Okay, so this solution certainly doesn't do what we wanted, and what we wanted to not buy too much milk. Okay, so how do we do that? Well, obviously, we want to, we can, the problem here is that in some sense, both person A and B execute the same instructions and, so to speak, take the same actions without kind of any coordination. They execute that kind of code, each of them at the same time, right? And so what we want only one person of the two to go to the store to buy milk, right? So basically, you can see now the concept of critical section. If you think about the program as going to the fridge, going to the store to buy milk, we want only one person to do it, right? And one way to prevent that, like we learned and we saw also last time, is to have locks. So you lock before entering the critical section and you unlock after leaving the critical section, okay? Now, the one important thing which will come over and over again, and what makes the implementation of locks challenging is that any lock implementation or synchronization, primitive implementation, involve waiting. And why is that? It should be obvious, right? Because if many threads wants to enter the same critical section, and only one at a time can do it, this means that one will go and in a critical section, and the other ones, what they can do? They have to wait. There is no way around it, right? So remember about. So of course you can, one way to do it is to lock all the way also the fridge, and basically, you go to, before you go to the store, you lock the fridge, and if the other person sees, come to the fridge, it's locked, it is not going to, it's going to wait for you to unlock the fridge. And then this guarantees that it's only one person, you buying the milk. But of course, this is not ideal because, what if the other person wants something else than milk from the fridge? So this is kind of very coarse grained solution. Okay. So let's see how we are going to solve this problem. And before doing that, it's like, this is a tricky problem. And this general, these problems, when concurrency problems, are tricky. And they are tricky fundamentally because there are many entities doing the same things at the same time. And it just, as a humans, we are more used to thinking linearly than thinking, about many things happening at the same time. We are not very good at that. So that's one of the reasons. And you can very well miss different, edge cases. So what you want when you have to deal with this kind of problem, actually, you want to do that when you deal with any kind of problem, programming problem, but in particular with this kind of problems, you need to be very careful and think quite a bit about what you want to achieve and how to develop a solution to meet those, the requirements you want to achieve. Okay, so don't start to code first. Just think first. So, and again, the way to think about it is to write down what you want to happen, right? So, and what do you want to happen here, or what are the correctness properties? So you want no more than one person buys some milk at a time, right? If two person buys milk at a time, you end up with 2 bottles of milk. At the same time, if there is no milk, there must be someone buying the milk. Otherwise, you don't get the milk. Okay. So and let's think about, if you restrict yourself to just load and store. So load and store meaning that you are going to modify some variable in the memory, right? Which can be read by any program. Okay. So so here is one example, and the way we are going to emulate this load and stores in this problem is through nodes, right? You put a node on the fridge with the message. This is basically, it's equivalent to storing, and you read the node, obviously, and it's equivalent to its load. So let's say what we have here, we have 2 nodes, 2 kind of nodes. One, and one node. And then what is a code? One possible code can be, one of possible solution is like, if there is no milk, right? And there is no node, we assume here that a node indicates that someone else is going to buy the milk. Then you leave node, and you yourself go to buy the milk, and when you come back, you remove the note, right? Simply enough. Okay. So what can happen here, right? Do you think it's a good solution? Okay, let's see now answer here. It's not a good solution, right? Oh, okay, we have an answer. Not atomic, that could cause problems. Yeah, there are problems here. And the way to look at, again, with people, this can work. But if this is done by machines, the machines are myopic. They only see these instructions. They only nothing else. So let's see what can happen. And always in these concurrency problems, the bad things can happen if somehow the instructions are interleaved in an unfortunate way. Okay. So let's see here what can happen. So let's say you have thread A and thread B. Now, thread A is looking and check for the milk. And then once thread A checks for the milk, it's context switched, is suspended by the operating system, by the scheduler. And thread B start to execute. And thread B is again, check for no milk. And in both cases, the answer is true, there is no milk, right? But after, and then thread B is check for the node, okay? And there is no node. But after checks from the for the node, again, we context switch to thread A. Thread A check again for the nodes, and there is no node, and leaves the node, right? Buy milk, remove node, and thread B is going to do the same thing, right? Because from the point of view there is thread B, there was no milk, there was no node. And from the point of view of thread A, the same was true. When it checked, it was no milk, and when it checked, there was no node. Okay, so you have now both thread A and thread B buying milk. Any questions here? So it's too much milk. This happens occasionally, right? If you don't have this unfortunate order of execution, actually this code will work. And the problem is this, when happen occasionally, is that, you know, you may say it's good news, right? It's like, it only happens from time to time. But the problem that when this happens, it's very hard to debug because it's not happen all the time, right? And that's what also makes these problems or this program frustrating, because they are very hard to debug. Another reason to think very well before starting to code. Okay, so how do you solve this problem, right? So clearly, you know, this node is not exclusive enough. And one solution you may saying is, because it's not, why don't we place a node first, right? What if we do this code, right? Right, instead of checking for the node, leaving the node before buying the milk, let's leave the node even before we check for the milk. What about this code? Any problem with this code? Yes, this is a very actually this is a pretty stupid code, because if you leave the node here, then if no node will be always true, right? And you know, sorry, if no node will be always false and no one will buy milk, right? So if you leave the node, right? If you leave yourself the node, and then you check for the node, there is a node, so you don't buy milk. That's why I was saying this is stupid. So it won't work even for one user. Okay. So let's go to solution 2. So this kind of didn't work. Maybe we need to be more sophisticated. Maybe we need to have two nodes, right? One for each person. Okay. So let's rewrite the previous code. So thread A, leave node A. Thread B, leave node B. And thread A checks whether thread B left a node. And thread B checks whether thread A left a node. Okay. Seems more sophisticated, may work maybe. What do you think? Is it going to work? Okay, why don't you guess? Okay, you don't need to tell me even whether, why is going to work or not. Just take a guess. Yes, now, good answer. I hope that this answer is not given because you looked at the next slide. But anyway, so now it doesn't work. And here is the reason, an example. It's about how these instructions are interleaved from thread A and thread B. You leave node A, you leave node B, thread A leaves node A, then we context switch to thread B leaves node B, is check for if there is no node A, and basically there is a node A, so this is false, and this is not going to execute it. And at the same time, thread A is looking whether there is a node B, and there is a node B, so this is really false. So it's not going to execute the if, what is under the if condition. And at the end, both of them remove their own nodes, but no one bought the milk. Okay. Make sense? Any questions here? Okay. So it's again possible for neither of the thread to buy milk. And it's again, this is really, really hard to debug because it happens rarely. So now let me tell you, I told you something initially about any synchronization primitive should involve something. And actually, even without reading the code, you could have answered the question whether the code is correct or not. Can you tell me why and how you could have answered this question immediately, whether the code is correct or not? Actually, the question is more clearly, you could have immediately see that the code is not correct. Yes, Nicholas, that's true. There is no wait. I told you that fundamentally any of these synchronization primitives has to involve a wait, because if someone is in the critical section, the other one thread has to wait if it wants to go into the critical section. There is no way around it. It's fundamental. But so far, none of these codes has a wait instruction or something equivalent. So that's why you can immediately say, this code is not going to work. So finally, okay, so let's go. Obviously, if no one gets the milk and and this continues, and obviously this is called starvation. We're going to learn more about starvation in a few lectures. So now finally, here is solution 3. There are 2 nodes, but notice thread A, it has a while. A while, this is a waiting instruction, basically. Because you wait for the node B. If there is a node B, then you wait until the node B is removed. Okay. So in other words, thread A will not execute, will not buy the milk, will not even look at whether there is a milk in the fridge. If thread B, it's checked and already went to buy milk. Yeah, testing set, it's a synchronization. So the question is from Michael, instead of waiting, can't we skip the critical section? Do we consider test and set as having a critical section? The test and set, they are going to be used to implement things like locks. That's it, right? And you need to have a while in order to wait on a test and set. Okay, so Akshay's answer is correct, right? So you need test and set alone. You need to also have, again, a while be around it. You'll see that. Is it going to work? Yes. And how you do convince yourself? You see, these are these 2 points, X and Y, in each of these thread programs. And what you say here is that at X, if there is no node B, there is safe for A to buy, right? Okay. Safe for A to buy, sorry. Yeah, right? Because if there is no node B, the thread B will for sure is outside this section of code. So for sure it does, thread B doesn't buy milk. So it's safe for A to buy if there is no milk. Now, if I am at Y, if there is no node A, it's safe for B to buy. Why? Because if there is no node A, this means that thread A is not executing this code, so we cannot buy milk. Here is another way to look at it. There are these 2 actions, leave node A and no node A when it's checked. So if leave node A happens before no node A is checked by the second thread, right? Then it's obvious that thread B will not buy milk because there is a node A, and it's also obvious, at least for now, that thread A will wait because there is a node B, right? Now, at this point, now the thread B is again, there is a node A, so we skip buying milk and then go all the way and buy and remove the node B without doing anything, without buying milk. But notice now what happens with thread A. Once thread B removes node B, thread A exits the while loop. It checks whether there is no milk, and there is no milk, and buys the milks. Okay? So in this particular case, thread A bought milk. Now let's assume that if node A happens after thread B checks whether there is no node A. What happens in this case? Right? So thread B found no node A. There is no milk, so it's going to buy the milk. And then it's removing the node B. As in parallel, node A is going to execute while node B and is going to wait for A to remove node B. When that happens and B node thread B removes node B only after it boards the milk. So now when it removes node B, this means that thread A will exit the while loop and now check for the milk. But now there is milk in the fridge because B put the milk in the fridge. It bought the milk. So therefore, A will not buy milk. Okay? So we are done. So you see, in this case, in both cases, only one thread and exactly one thread bought milk. Okay? So the solution immediately protects a single critical section piece of code. And this is the critical section. If no milk, you buy milk. Solution 3 works, but it's not very satisfactory. It's pretty complex, right? Even in this simple example. And like you see, we got, like what, 5-6 instructions. And it still took us like whatever, 10-15 minutes to convince ourselves that it's working. And also A's code is different from B's code. What if you have not 2 threads, but 3 threads or 10 threads, right? And finally, yes, we have a wait here, but it's busy waiting, right? This thread A consumes the CPU resources while waiting. We don't want that in general. So let's look for better ways. So think about lock interface you are considering. You want to acquire the lock and release the lock. These are the instructions. If the lock is taken, you are waiting in the acquire until someone releases a lock. Okay? And then your milk problem is very simple. You acquire the lock. If there is no milk, you buy the milk, and then you release the lock. This is like our very first solution with a lock, right? A physical lock to the fridge. But now imagine that you can put the lock only on something in the fridge where contains only milk, right? On a container in the fridge or contains milk. That's equivalent, right? So now the question is, how do you implement lock? This is what we are going to discuss. Remember, all synchronization primitive involves waiting. But you don't want to do the busy waiting. Just, spending the CPU resources while waiting. Instead, you want to sleep when you wait, and you want to be woken up when you can acquire the lock and enter the critical section. Solution 3 from the milk, our milk 3 solution, was basically equivalent to using atomic load and stores. Again, pretty complex and error prone. So now the question is about how we do this, implement the locks, because I saw that if we implement the locks, the solution is much easier. So one way to think about is to implement it in hardware. However, if you implement it in hardware, a lock, it turns out that it's pretty complicated. And there are some processors doing it, but it's again, the complexity is high and it's also slow. And because the chip is more complex, it's actually slowed down many other instructions. So one simple solution to implement it with what you know, learn so far, it's about using the interrupts, right? Remember that we have these interrupts, external interrupts, internal interrupts, but fundamentally the interrupts, when you execute an interrupt, you are, you are going to run some code. And what we are talking about here is that, think about like local acquire, you disable all interrupts. So this means also there is no context switching, because in order to have also the context switching, you need to have the timer interrupt, right? Or the interrupt, another interrupt, external interrupts to do it. And the log release, you enable interrupts. So this is, so what is the problem with this approach? Is not going to work, right? Before, if you acquire an interrupt, right? If you do acquire a lock and you disable all the interrupts, and then you do something like a while true, you hang, the computer hangs. It's again, it cannot be interrupted, right? You need to do something like yield to voluntarily provide, give access to the scheduler in order to the kernel to schedule another thread. But this code will lock the entire computer. So it's very, very risky, right? You don't want to do that. And there are many other reasons, like for real-time systems, there is no guarantee of timing, because the critical section can be arbitrarily long. And obviously what happens when there are very important IO events, right? So let's think about a better implementation of the locks by disabling interrupts. So here is one. So basically you maintain, there's a way to think about, you use a lock to implement a lock, right? And what you want is that when you the segment, you want to minimize the code between disable interrupt and enable interrupts. That's what you want to do. Okay? Because the problem is in the previous case, the problem is that you disable interrupts and you enter the critical section, then the critical section can be arbitrarily long, right? Depends on the application, right? But in this case, we are going to implement the lock with a disable interrupt and enable interrupts, and then expose acquire lock and release lock to the application, implemented under the hood by the disable interrupts. But notice here, the disable interrupts and enable interrupts, you have a very small piece of code here. So it's going to run very, very quickly. Okay. So ideally what you do for the acquire, so say the value is a lock value, and it's either free or busy. So to acquire it, if you disable the interrupt to manipulate this value, if the value is busy, what did we say? We want to sleep. So put thread on the wait list and go to sleep. And somehow you want to enable interrupts. Okay. So other thread can execute, right? Else, you acquire the lock, value is busy, and you enable interrupts. Okay. And for relieves, you disable interrupts. You look if there is only anyone on the wait queue waiting for the lock. If it is, you give the lock to one of the thread from the wait queue, and you place that thread on the ready queue, so that thread can execute the critical section. If there is no one on the wait queue, the value is free, and you enable the interrupts. Okay. So you see here, the wait happens because you put the thread waiting on the waiting queue, and then you take that thread from the waiting queue when another thread released the lock. Any questions here? So now it's what I was saying. You increment a lock by another lock, right? And the reason for that, because the second lock you are going to use, you can use disable and enable interrupts by making sure that the critical section protected by disabling and enable interrupts is very short. And this can be implemented by the operating system. So you have control about on the length of the critical section protected by the interrupt disabling and enabling. Okay. So that's the main difference from using disable interrupts and enable interrupts directly. Okay. With this design, the users can take as long as they want in their critical section, right? Because their critical section is not protecting by disable interrupt or enable interrupt. Now, what is a big problem? Here is a big problem. We need to enable interrupts when we put the thread on the wait queue, because we need to allow other thread to execute, in particular the thread which is in the critical section. But the question is, where do you need to install to enable the interrupts? There are three possibilities. One is here, before putting the thread on the wait queue. It is correct. Okay, let's, it's not, because the release can check the queue and not waken up the thread, right? So enable, you put the enable interrupts here. Before the thread is put on the wait queue, you do context switch. You can do context switch to the thread, another thread, which is executing the release, right? And the release is going to look at if there is any thread on the wait queue, and there is none, because acquire didn't have a chance to place the thread on the waiting queue. So the thread will not be open. What if you put the enable interrupts before go to sleep? These are correct. So here is a question, Michael from Michael. Does if have to be replaced with while? No, I'll let you know why, because, okay. Let me go through this slide and I'll tell you why after that. No, because this is not correct either, because release puts the thread on the ready queue, but the thread still thinks it needs to go to sleep. Okay, so you put the thread on the waiting queue, you enable interrupts. Now assume that the release of from the other thread is executed, right? And here the release is looking on the wait queue, and you have a thread on the waiting queue, and take that thread to execute it. But then when the thread is executed, it goes to sleep. So it don't execute. Now to the question. I said that it's a busy, that we need to have some waiting for any synchronization primitive. You need to have waitings. So why we don't have a while here? The reason we don't have a while here is very simple. Like I mentioned, but probably I was not very clear. It's because the waiting here happens implicitly by acquire. If the lock is busy, you put the thread on the waiting queue. Putting the thread of the waiting queue, that act means waiting, right? It doesn't happen in the program. It happens in the kernel, right? You put the thread on the waiting queue and the thread will wait until a release is going to be executed, until the lock is released. Okay. Anyway, so in order to solve the problem, you need to release a lock after going to sleep. But how you do it? Because the thread is sleeping, so how can you execute an instruction to enable the interrupts? Any suggestions? So the problem is very simple, okay? It's like, I want logically to enable the interrupts after I go to sleep. But how can I do that? Because I'm sleeping. Modify sleep instruction, sleep function, Aaron. That's good. But, you know, I need to, how you modify that? That's not easy. You can try it, but you'll see that it's not easy because you still have a bunch of instruction, and you'll see the same problem like you have here. Have the kernel do it for now. Yes, you can have the kernel do it for now, but how do you do it? You do it on whenever you do the sleep. That's not good, right? Because you can call a sleep in different other, you know, for many other cases. So actually the solution is quite brilliant, in my opinion. If the thread which go to sleep cannot enable the interrupts, the solution is that another thread which wakes up is going to enable the interrupts. So you do it on context switching. And in some sense, you can argue this is done by the kernel. You can do that in the kernel. But this is a solution here, right? So, and the nice thing about the solution is, again, is like, if the thread which goes to sleep cannot enable the interrupt because already went to sleep, the solution is for a next thread, which when you return from the sleep, to enable the interrupts, right? So you have another thread enables the interrupts. Okay. So this is pretty nice. So when you wake up, you enable interrupts. Okay, some announcements. Design review schedule as soon as possible. You haven't done already. The review is your TA. Needs to be done by this Thursday. So you have 2 days. And show up on time listed. There is no Berkeley time. We have, you know, now 10 minutes after. Midterm, it will be between 7 and 9 p.m. 8 days from now. We are going to cover everything up to and including the next lecture. There will be a midterm review on Monday between 7 and 9. And for logistics on proctoring policies and so forth, cheat sheet, look out for the posts. Let me see. Sorry, it's 29, what I'm saying here. Wednesday, 9/29. Thanks for catching. So question here was, how do you can context switch? Because here, everything disabled, the interrupts are disabled. So here we are not talking about context switching based on the timer event. We are talking about here. This is here. Let me just show the code. So this is a code, right? You see this part where if anyone on the waiting queue, so when you do this, you go to sleep. By the go to sleep means you yield the control to the kernel, okay? And the kernel, the interrupts are, you are going to, execute this instruction and take the thread of the wait queue. And when you do this, you enable the interrupts. Okay. So this enable interrupts from here. I hope that you are seeing what I'm highlighting. Is going to have, it's going to happen here. You take the thread of the wait queue and you are going to, you return from the, this means you return from the sleep and you are going to enable the interrupts just before place on the ready queue. Okay. Hopefully it answers the question. Okay, so let's see how here, and we have another 20 minutes. So here, this gives you a sense about how this is working, doing a kind of a simulation. So here is lock acquire. We have a release. This is a code. And we have two threads executing the code, thread A and thread B. Each of them is doing lock acquire, go to critical section, lock release. And let's say thread A acquire it. It disables the instruction. It disables the interrupt, sorry. The value, so in this particular case, someone has, no one has a critical section. Yeah, so this is the first thread A, which look execute acquire. There is no one using the critical section, so the value is 0. Increments the value to 1, which means that it acquires a lock and it enables the interrupts. And now you are in critical section, right? This is what happened, right? At the same time, let's assume that while you are in the critical section, thread B is starting to be executed. Again, while you are in a critical section, the interrupts, the interrupts are enabled. Thread B is going to start running. Thread A in the meantime, it's in the ready queue. This is just context switching, traditional context switching. You do the lock acquire, execute lock acquire. But now you look and what you can see is the value it's 1 because the lock is acquired by thread A. You cannot acquire the lock. B cannot acquire the lock as well. So you go to sleep, right? So you are going, thread is going to be waiting. It's going to be on the wait queue. Okay. And now you are going to start executing thread A because it's ready to execute, and this thread B went to sleep, and thread B when is going to sleep is going to voluntarily, release the CPU. Okay. So the kernel is going to start executing thread A, resuming the execution of thread A in the critical section. Critical section ends, and then it's releasing the lock. Okay. And now, if anyone waits on the waiting queue, is anyone waiting on the waiting queue? Yes, it's thread B, right? So thread B is placed on the ready queue from the waiting queue on the ready queue. And now you enable the interrupts. You are done. Thread B is ready to execute. And then next time you are going to execute thread B. Okay, and thread B executes, acquires the locks, and continue and enter the critical section. Okay. So please go and try to go carefully through this example. Any questions? Okay. So what is the problem? So it is working. Yes, it's working. But there are several issues. You cannot give lock implementation to users. They are going to make mistakes. And now, okay, you can solve that by saying the kernel can do it. And that's a very valid answer. But the other problem, especially with the interrupts, is that it doesn't work well on multiprocessors. You have multiple cores which execute in parallel, and all cores can access the memory. So therefore, the value of the lock. So what you need when you need to disable the interrupts, you need to disable interrupts on all the cores. You need to send messages between cores to disable interrupts or enable interrupts, which is very expensive. The alternative to this is to have atomic instructions, right? And typically what they do, they read a value and write a value atomically. So instead load and stores, only is reading a value is atomic and writing a value is atomic. But this adds another element. The read, you can have a read and write, which are atomic, like one operation. And these are great. They are working both on uniprocessor and multiprocessors. And yeah, they are quite simple. And here are a few of them. The first one is test and set. Okay. So what is doing? Test and set, read a value on the particular memory, the value at a particular address, and returns it, and also at the same time set it to 1. Okay, so reading the value, setting it to 1, and returning the previous value, the value before was set to 1, original value, is atomic. Okay, that's it. That's the atomic instruction. So you see there are multiple operations in this which are atomic, which are in this atomic instruction. Then it's a swap. And a swap is basically what it's doing, right? You get a value. You put a value in a register, and that value you put in the register is going to be swapped with the value at a particular address. Okay, this is what it is. So you give a value in a register which is going to be swapped with a value at a particular address. And finally, is compare and swap. This is a little bit more complicated. You give 2 registers here, and if the memory address is still equal with register is still equal with register 1, then you put the memory value in register 2. Otherwise, you don't change the memory. Right. And these are, x86, obviously it's Intel. 6800 was a very popular chip, Motorola chip, which was the chip for use by Apple, early Apple and Macintosh computers. And test and set, it's actually in most architectures today. Okay, so here is an example about how to use compare and swap. Okay, and this is about how you are going to use to insert atomically a new element as a head of a queue. Okay, this is what you want to do it. This is enqueue operation. So insert a new element as the head of the queue. Okay. So here what you do it. First of all, you have a while. Do you see? Do until. Right? It's a loop. Okay. And in the loop, in the condition to exit from this loop, you compare and swap R1 and object. Right? Object is the object identifier. R1, you can see, is a root address. Okay. Okay, so it's the original root, right? So what happens here is basically you are going to wait until, so what you do here, you set the root to the new object. Okay. And then you are waiting until the root is pointing, sorry, what you do is the following thing. You set the next object, the object to point to the first element in the queue, this one. Okay, this is what you do, right? So this is, you get the pointer from the root, which is a pointer to the first element in the queue. Then you set the object to point to the new object to point to the old first object in the queue. And then you are going to use a compare and swap to move the pointer of the root to the new object. And you wait until that is done. Okay. So that's what happens here. Now, how we implement lock, switch, test and set is very easy. Acquire, you set up the value to 0 here. And acquire, it's you just wait for test and set to be 1, right? And then release value, you just set value to 0. Okay. So what happens here? Remember, what does test and set is doing? The test and set is going to read, to return the value and set it to 1 in one instruction. If the value is 0, you return the value to while. So while is going to exit and set value to 1. So it's great. So lock is not busy, you acquire the lock. If the lock is busy, so value will be 1. You are going to set the value to 1. It's already 1, so nothing will happen, but you return 1. So you are going to be stuck in the while loop until the release is going to be executed and the value is set to 0. Right? So it's quite elegant, right? Obviously, the problem here, you have the while, you do the while in the program, right? So very inefficient, right? So you don't want to do that. But this is a correct implementation, very simple implementation. So you see how test and set allows us a very simple implementation of the locks, right? And again, the test and set, very easy to remember. You do 2 things. Return the value and set is to 1. That's all. Okay, so the problem is busy waiting. Of course, busy waiting, again, it's a correct implementation. The machine can still receive interrupts. The user code can still use a lock, work on multiprocessors, all positives, but of course, you don't want this busy waiting. It's inefficient, also can result in what we call priority inversion, right? If the busy waiting thread has a higher priority than the thread holding the lock, right? So this is another way to think about it. Oops. Another way to think about it is like you have two threads and one has higher priorities than the other one. Higher priority is going to be always executed before the other one, the one with a low priority. And now the thread with a low priority is going to have the lock. If the thread with a lower priority has a lock, the thread with a higher priority will be stuck because it's going to be stuck in the while loop, and the thread with a lower priority cannot execute because the thread with a lower higher priority, but because the thread with a lower priority cannot execute, it cannot exit the critical section, it cannot release a lock. So this is priority inversion. And this happened in many cases. So that's the problem, right? And so we really want, because we don't want us to, you know, this busy waiting, we need to find another solution. And in general, when you have the homework problem or exam solution, unless otherwise specified, you should avoid busy waiting. Okay. So now let's see for the next couple of minutes, think about maybe better locks using test and set. So the question, can we use test and set to implement locks without busy waiting? And the answer here, we cannot, but we can minimize the busy waiting section. And again, the solution here is like with, if you remember, with interrupts. We use a lock to implement a lock in some sense. So the lock we want to implement is value. It's called value, okay? And then what we do, we protect the critical section of the acquire and release, the critical section being the one which modifies a lock, which is value, by a test and set. Okay? So use a test and set to implement and protect these critical sections, you know, acquire and release. So the solution is very simple. We have defined another variable, which is called guard. This ensures the mutual exclusion for these critical sections, which are in the acquire and release. Okay. And while we initialize to 0, so while guard, if guard is 0, then you are going to acquire the lock. So while will exit, right? Because remember, testing set returns the current value of guard, that is 0, and set is to 1. So you exit the while loop, and then you set up the value, right? What we know. And the release is the same. You protect the critical section by test and set. And then here you have the same problem like with the release interrupts. When you go to sleep, you also need to set a guard to 0. Then when you need to set up it up, right? But this will be much easier. Okay. So, and when sleep has to be sure to reset the guard variable, right? And we are going to end up here, this lecture. On this note, we are going to continue next time. And you should think a little bit about this code. And there is a question here, why, oops, let me see. Okay, I'm going to stop here because for some reason I lost my pointer, so I cannot see my pointer on the screen. So there is a question at the end of the previous slide. Please think about it until the next time. without looking at the next slides. And there is, yeah, there is a question here. If while test and set, so we are, the lecture is done. I am going to try to ask the last question, which was on the chat, and we'll meet next time. So for people who want to hear the answer can stick around. And the question here is that from Michael, it's while test and set val, you yield critical section, and then val is 0. And then you set up val to 0. Yeah. I think that should work. So, yeah. If you, that should work. That should work. The problem here, though, that if you yield, then you are still going, you yield the processor, you are still going to be woken up before the lock it's available. Okay, so for instance, again, it's like you yield the processor to for another thread. That thread can execute. It may not be necessary. The thread who has a lock. When that thread finishes, or when a time quanta finishes, you are going to be woken again, and so forth. So it's still not as efficient. It's better than just doing busy wait, but it's not as good as putting the thread on the wait queue and being woken up only when the lock was released. In this case, you are going to be woken up multiple times. Okay, so with that, I'll see you next time. Thanks, everyone.